Hi everyone. So in this question we're going to be covering some A-level further maths complex numbers. So for part A, what they want us to show is that the left hand side can be written as the right hand side. So the first thing we want to do is expand the two brackets. So it's going to be 1 minus a quarter e to the minus 2I theta minus a quarter e to the 2I theta plus 1 over 16. So we can simplify a bit here. It's going to be 17 over 16 minus a quarter e to the 2I theta minus a quarter e to the minus 2I theta. Now what we want to do is we want to change our exponentials and we want to write it in terms of sine and cos. So what we can do is use Euler's formula where e to the 2I theta is equal to cos 2 theta plus I sine 2 theta. So what you do is you plug this into here and then change the argument to minus 2I theta, and then you can plug that into here, and then once you simplify everything it should turn out to give you this. But what I want to show is by using the exponential form of cos 2 theta and plugging that in to get your answer, which should be the same. So cos 2 theta equals to e to the 2I theta plus e to the minus 2I theta. So I want to kind of get this form over here. So I'm going to do a bit of factorizing here between these two. So it's going to be equals to 17 over 16 minus a quarter of e to the 2I theta plus e to the minus 2I theta. So I can see that this bracket is equal to this bracket, just got to multiply the two up here. So I've got 2 cos 2 theta, which is equal to e to the 2I theta plus e to the minus 2I theta. So now I can plug that whole thing into here. So it becomes 17 over 16 minus a quarter 2 cos 2 theta. Once I expand it, I should get 17 over 16 minus half cos of 2 theta. Now what I want to do, I can clearly see that here they have force factorized 1 over 16 out, so that's what I want to do. I want to deliberately take out 1 over 16. So if I take out 1 over 16, that will become a 17 here, and if I've taken out 16, I've basically multiplied this by 16, so it should be minus 8 cos 2 theta. So this is the way that is not shown in the mark scheme. In the mark scheme they show it using Euler's formula, but I just wanted to show how to do it using the exponential form of cosine. And that's part A done. So part B should be a fairly straightforward question. They've given us a series and they have said that it has a sum to infinity, and to express this sum to infinity in terms of e to the 2I theta. So from inspection you should be able to see that it is a geometric series. So we can see that the first term a is equal to e to the 2I theta, and in the common ratio just kind of divide the second term by the first term, and it is a quarter e to the 2I theta. The sum to infinity formula is equal to a over 1 minus r, and we've just got to plug it in, so easy 2 marks there. So the final answer should be e to the 2I theta over 1 minus a quarter e to the 2I theta. Now you can try and simplify this if you want to, but I wouldn't recommend it. You'll see in the next couple questions why, but it doesn't tell you to simplify in any way, so just leave it as it is. We've answered the question. Part C can be quite a tricky question for most students. They want us to work out the infinite sum of a trig function like cos or sine. Most students don't know where to start here, but I tell my students that when you're doing an infinite summation of a trig function like cos or sine, you want to first work out the infinite sum of e, something that has e in it. The reason why is because we can use Euler's formula then to break down e into cos theta plus I sine theta, where you have two separate summations you can form, one being a real part, which is generally cos, and one being an imaginary part, which is sine. Okay, so before we do that, we need to first figure out how to get an exponential summation in sigma notation. So what we can see here is we have hence written down here. Hence basically tells us that we want to use one or more of the previous answers. So as I said, we want to work out a summation in sigma notation in terms of which has e in it. This looks like part B, looks like it's going to be something we want to use. Okay, so that's why I've written it on the right hand side. To write it in sigma notation, we need to write it in terms of its nth term form. Okay, so I've got A as this, R as this from part B, and I want to work out what the nth term formula is, and then I have e to the 2i theta multiplied by a quarter e to the 2i theta to the power of n minus 1. So doing a bit of expanding, it's going to be 1 over 4 to the power of n minus 1 e to the 2i theta e to the 2i n theta minus 2i theta. Okay, so what we can see is when we multiply these two together, these two powers cancel out, so you're just left with the 2i n theta. So we have a 1 over 4 to the power of n minus 1 e to the 2i n theta. So now we can write this in sigma notation. So that will be n equals 1 e to the 2i n theta. Now we want to break it down using Euler's formula. Open bracket cos 2n theta plus I sine 2n theta. Okay, now from here we can break them down into the two separate summations, one being the real part and one being the imaginary part. Notice how what we have here is the same as what they want us to work out. So we know we're doing something right here. Plus, we can put the I outside. Oops. N equals 1 to infinity of, it should be a quarter. So 1 over 4 to the power of n minus 1 of sine 2n theta. So we don't want to deal with this part yet. We want this. Okay. But before we do that, what we need to do, we need to express this without the sigma notation, which we have actually done in part B. Okay, so what that will be is e to the 2i theta. It's just the answer from the previous question. A quarter e to the 2i theta. Now what do we do next? Most students do kind of get stuck here, but what I'm going to do here is actually times the top and bottom by this. You might be asking why. Well, this is something that we've done in part A, and we know it looks like this. Okay, so we're going to copy that as well. So the bottom part should be that, and the top part we just expand out as normal, and we see what we get afterwards. So that would be e to the 2i theta minus a quarter at the top, and at the bottom we're going to write 1 over 16 17 minus 8 cos 2 theta. Okay, times top and bottom by 16, and then we get 16e to the 2i theta minus 16 divided by 4, and then we get 17 minus 8 cos 2 theta. So we can see we've got the denominator. Now we've got to try and figure this one out. Now you can see that e has come out again, so we need to break down the e into cos and sine, so we get the complex and the real and imaginary parts out of it. So that will be 16 cos of 2 theta plus 16i sine 2 theta minus 4, all divided by 17 minus 8 cos of 2 theta. Okay, so now that I've got this, what I want to do is just break them into two separate fractions. So 16 cos of 2 theta minus 4 over 17 minus 8 cos 2 theta plus, and I'll put the I outside like that, and then 16 sine 2 theta over 17 minus 8 cos 2 theta. Okay, so now we can see when we've got the two summations now, we can compare the real part here, which matches the first part of this sigma notation, and then we've got the imaginary part here, which matches the imaginary part of the sigma notation here. Okay, so our answer, we wanted this, so we've shown that now. Okay, part D should be straightforward since we've done all the hard work in part C. They want us to deduce a similar expression for the infinite summation of sine. Okay, so what we can see from our previous answer, this is what we want to write as our final answer. Okay, so that's what we've got to write. So it's going to be 16 sine of 2 theta over 17 minus 8 cos 2 theta, and that's the end of the question.